Welcome to today's explainer. Okay, let's dive right into this. We are taking a magnifying glass to one of the most notoriously tricky, but honestly incredibly rewarding areas of the Cambridge Igcse Additional Mathematics syllabus. Yep, subject code 0606. We are looking squarely at modulus equations. Now, if you're sitting for AdMath, you already know the stakes are pretty high. This isn't just about crunching numbers, it's about showcasing a really profound understanding of mathematical logic. And modulus equations? They are the ultimate test of that logic. Today, we aren't just going to look at how to solve them. We're actually going to reverse engineer the examiner's playbook so you know exactly what they want to see on your exam paper.
Take a look at this insight, straight from the senior examiners. The difference between a B and an A star in additional mathematics often comes down to modulus equations. Wow, that is a massive statement. And what it tells us is that our goal in this explainer isn't just about scraping by, right? We are aiming for that top-tier grade, the A star, by decoding exactly what the examiner is looking for. Modulus questions basically act as a gatekeeper. If you can master these, you are signaling to the examiner that your algebraic reasoning is absolutely elite. So how do we actually cross that threshold?
First up, we need to know what we're up against. We're tackling these 4 specific algebraic and graphical modulus equations today. We've got the standard linear modulus equal to a constant, where c has to be greater than or equal to 0. Then we escalate. A modulus equal to a linear expression, a modulus equal to another modulus, and finally, the quadratic modulus equal to a constant. Just take a moment to really look at these. They pack a lot of visual and algebraic complexity. When you see those absolute value bars, you shouldn't just be seeing a positive number machine. You should be visualizing sharp V-shaped graphs bouncing off the x-axis, intersecting with straight lines or parabolas. The examiner uses these specific formats for a reason. They're perfectly designed to trap the unwary student who's only relying on surface-level algebra.
So the absolutely crucial point here is that tackling these equations successfully requires an understanding of their theoretical architecture. These aren't just random algebraic symbols tossed onto a page to confuse you. They rest on a very strict underlying foundation. Well, what do we mean by that? We mean precise definitions, knowing exactly what the modulus function represents in terms of distance from 0. We mean causal relationships, understanding that if you say square both sides to remove a modulus, you might actually cause extraneous solutions that aren't real. And we mean cross-topic integration. Examiners are testing whether you can take the strict rules of algebra and apply them to geometric and graphical realities. They are testing very, very specific cognitive skills.
And this architecture builds directly into the examiner's grading rubric. There are 3 distinct cognitive domains examiners are actually grading you on when you're solving these modulus problems. First, knowledge and understanding. Simply put, can you recall the exact definition of a modulus and the correct formatting? Second, application. And this is where a lot of students stumble. Can you take that pure mathematical definition and apply it to a completely unfamiliar, complex context on the exam? And third, analysis. Can you evaluate alternatives, like deciding whether an algebraic method or a graphical method is the most efficient route for the specific question sitting right in front of you? When you write your answer, the examiner is literally ticking off these 3 boxes in their head.
Understanding those cognitive domains is great and all, but let's be real. How do we turn that theory into undeniable marks? Because if you don't translate your understanding into the exact language the examiner expects, you're going to lose out. So let's transition from the theory to the practical methodology you absolutely must deploy in the high-pressure environment of the exam room. Okay, here is your secret weapon. This exact 5-step procedural framework will safely navigate you through any modulus equation. Step 1. Deconstruct the question. Are they asking for an algebraic solution or a graphical one? Look at those command words. Step 2. Extract the relevant data. Identify your equations, constants, and parameters. Step 3. Select your analytical framework. Are you going to square both sides or split it into positive and negative cases? Step 4. Execute with clear notation. Please do not skip lines of working. And finally, Step 5. Present with correct terminology. Make it abundantly clear which solutions are valid and which are extraneous. Stick to this structured process, and you take the guesswork entirely out of the equation.
This process is the core of what we call the method mark strategy. And let me reassure you right now, additional mathematics is not just about getting the final number right. Marks are heavily awarded for systematic analysis, evidence-based reasoning, and a really clear procedural process. The examiner literally wants to see your brain working on the page. By following strict conventions, clear annotation, proper headings if you're testing different cases, maintaining correct mathematical grammar, you secure those method marks. Even if you make a tiny arithmetic slip right at the end, a perfectly structured procedure ensures you capture almost all the marks available. Basically, show your evidence. But, of course, under exam conditions, things still go wrong. We've actually dug into the principal examiner reports for Cambridge 0606 to figure out exactly where students lose the most marks. And you know what? The examiners highlight very specific patterns of failure. So, let's lift the veil and look at the most common traps waiting for you.
Here they are, the top 3 examiner warnings straight from the grading room. First, using the wrong approach for the context. Like trying to purely algebraically solve a complex modulus equal to a linear expression problem, without considering that drawing a quick sketch would instantly reveal how many intersections, and therefore how many valid solutions, actually exist. Second, forgetting format and presentation conventions. Sloppy notation definitely loses marks. But the third one, this is the absolute classic trap. Providing generic answers that are not specific to the scenario given. Students memorize a routine, regurgitate it onto the paper, and completely ignore the specific constraints of the question they were actually asked.
And this brilliantly illustrates the difference between losing and gaining those final, crucial marks. A generic answer just blindly applies a formula. It might find 2 mathematical roots and just leave them there. A context-specific answer, however, takes those roots and tests them back against the original scenario. It recognizes that, hey, in a modulus equation, a negative distance is impossible. It identifies the extraneous root and formally rejects it, explaining exactly why based on the context of the specific graph or equation provided. Applying the right math in a generic way versus a highly contextualized way is quite literally the difference between a B and an A star.
Let's focus on the number 3 for a second. Why 3? Because higher-order questions in additional mathematics demand a 3-level framework of analysis from you. The examiner isn't just looking for calculations. They are looking for a descriptive level, an analytical level, and an evaluative level. Descriptive, what is the equation? Analytical, what's the mathematical process to solve it? Evaluative, does this final answer actually make logical sense in the real world of mathematics? To get the top grade, your brain needs to be firing on all 3 of these levels simultaneously.
Which brings us to the absolute pinnacle of mathematical problem solving, evaluating evidence quality. Truly mastering graphical or algebraic methods means analyzing how your own assumptions affect your final mathematical conclusions. Like, did you assume that squaring both sides preserved all the original constraints? Well, that's a limitation you need to identify. Are there alternative interpretations? For instance, maybe solving by finding the vertex of the modulus graph and comparing slopes rather than just doing brute force algebra. When you evaluate your own working out as you go, identifying where assumptions might introduce errors, you are thinking exactly like a senior examiner.
And if you want the ultimate secret to unlocking that A star, it's right here in this quote from the Principal Examiner report. Candidates referencing cross-topic connections achieve significantly higher marks. This is vital, guys. Modulus equations do not exist in a vacuum. You might need to integrate them with simultaneous equations, with coordinate geometry to find the intersection of lines, or with inequalities. The students who really thrive are the ones who realize that the entire additional mathematics syllabus is basically an interconnected web. When you can seamlessly pull in a concept from coordinate geometry to justify your solution to a modulus equation, the examiner knows you have truly mastered the subject. So we've decoded the theoretical architecture, the 5-step procedure, and the examiner's biggest warnings. I want to leave you with this somewhat provocative question to think about. If examiners heavily award marks for the analytical process and clear presentation, are your daily practice sessions focusing as much on how you present your work as they are on simply calculating the final answer? It's so easy to rush through past papers, right? Just checking the final number in the mark scheme and moving on. But the real growth happens when you practice perfect formatting, clear reasoning, and contextual evaluation every single time. I invite you to take this 5-step framework and apply it rigorously in your very next past paper session. Change the way you practice, and you will absolutely change your results. Thanks for joining me on this explainer, and keep pushing that mathematical logic to the next level.